If you could swim in the oceans of the Miocene 10 million years ago, it's possible that the last thing you'd see would be a shark fin 2 meters high approaching you. Or perhaps even worse, you could quickly be swallowed up in one bite by a predator from below without even having time to notice the attack. This is the famous Megalodon, the largest shark that ever lived and one of the heaviest macropredators of all time. But there's much more to it than just its size. Today we're going to understand many other aspects of their existence, such as their evolution, their environment, their reproduction, their physiology, their behavior, interactions with other species, and much more. With practically only its teeth to testify to its existence, paleontologists have to be extremely creative to infer anything about this animal. What's more, it's not enough to know that it's gone, we're also interested in knowing why and when. Join me to find out what we know so far about the life and death of the Megalodon. Of all the things that make Megalodon one of the most famous extinct animals after Tyrannosaurus rex, the most important is its size. The largest predatory shark today is the great white, which is 5 meters long and weighs 2.5 tons as an adult. But he's not the largest living shark. That position belongs to the whale shark, a giant filter feeder over 10 meters long. However, in the fossil record we have found evidence of an even larger shark, the Megalodon. Today there is no animal like it. Since all the largest marine animals such as whales and whale sharks are filter feeders, feeding on plankton and small fish in huge quantities. The only current predator that even remotely matches Megalodon is the sperm whale, the largest carnivorous animal today at 15 meters long. Its name perfectly describes its fossils and means giant tooth. Compared to them, the teeth of the modern white shark look like toys. The largest specimens easily exceeded 30 centimeters in length and are comparable in size to a human face. As we will see, every detail of these teeth is crucial to understanding the life of this animal, since they are practically all that remains. The diagnostic characteristics of a Megalodon tooth are its immense size and triangular shape, fine serrations on the sharp sides, a convex lingual or inner face, a slightly concave or straight labial or outer face, and a wide V-shaped upper part. Unlike most vertebrates, they didn't have real bony skeletons, being cartilaginous fish like today's sharks, rays, and chimeras. Cartilage is a much less mineralized type of tissue, and therefore much less prone to fossilization. Teeth, which are not made of bones but of other minerals with a different structure, are generally the most weather-resistant parts of any vertebrate. We know many extinct mammals, for example, only by their teeth, thanks to their high susceptibility to fossilization. Estimates of their total life size can vary greatly from study to study, with the most conservative pointing to a maximum length of 15 meters. Other studies using other comparative methods suggest that it might have had a more elongated body, reaching an impressive 20 to 25 meters in length. Weight estimates vary greatly depending on the body shape adopted. A weight of 30 to 60 tons for the largest adults is proposed, making it at least as large as a humpback whale in body mass. This is because these extrapolations are usually based on comparisons with the great white shark, which is the largest predatory shark we know of in our lifetime. However, this can confuse us. Although it seems like a great analogy for inferring various aspects of the Megalodon's life, these two animals may be much more different than we first thought. Some time ago, it was even proposed that the white sharks descended from Megalodon, but this hypothesis has now been vehemently dismissed. It seems that they are not only from different families, but may belong to reasonably distant lineages, having split up at the end of the dinosaur era. Almost 70 million years of evolution may have made these two animals very different, so we have to be careful when using present-day animals as reference. Apparently, Megalodon belonged to a family of sharks that is now completely extinct, which makes its study even more complex. The classification of this animal is a highly controversial topic among researchers. It has already been placed in the same genus as the white shark, Carcharodon, and in the same family as it, Lamnidae. More recent interpretations reject this proximity, proposing the genus Carcharodon in the extinct family Otodontidae. However, most studies place it in the genus Otodus, along with considerable diversity of other species from the same genus and family. The taxonomic consensus is that it belongs to the Otodontidae family, regardless of whether it's called Carcharodon megalodon or Otodus megalodon. This family, known as megatoothed sharks, is distinguished from the others by certain characteristics of its dentition, including the loss of the lateral cusps, the widening of the dental crown, and an increase in size over time. Long before they were described by modern science, these huge teeth were already known and interpreted in different ways by various peoples over time. The first written records that testify to the existence of the megalodon date back to the year 73 by the Roman naturalist Pliny in his book Historia Naturalis. In this work, he describes these fossils as something similar to an immense petrified human tongue, which they called glossopetri. Many believed in legends that these stony tongues fell from the sky during lunar eclipses. From the 12th century and for some time in the Middle Ages, these teeth were believed to have supernatural properties and were used as amulets and ingredients for spells. But they weren't the first to recognize the existence of these fossils. There is a lot of evidence of megalodon teeth that were modified and used by the native peoples of North America almost 3,000 years ago. They were shaped to be used as arrowheads, knives, and even pierced precisely to become jewelry, such as necklaces and pendants associated with funerary rituals. Because they were large, sturdy, sharp, and serrated, their use most likely saved the trouble of making the same tools out of stones or wood. Megalodon was finally recognized as an extinct species of animal in 1835, almost 200 years ago, by the naturalist Louis Agassiz. Since its discovery, Megalodon has become one of the best-known prehistoric animals, and one that arouses the most interest and fascination among the public, partly because of the hundreds of products and media that use its image to inspire fear, such as horror and science fiction films, series, stories, toys, among many others. But little is known about their biology, behavior, environment, and extinction. Their image has been reduced to an insatiable and cruel killing machine, where we're going to understand that they were actually intelligent, complex animals and sensitive, sophisticated predators. There's evidence that Megalodon is the last species in a sequence of chronospecies of the genus Otodus. This means that these species have a direct relationship of ancestry and descent and have replaced each other over time in a sequence of anagenetic speciations, when one species gives rise to another species without bifurcations in their genealogy. Interestingly, it was possible to observe a slow and steady trend towards increasing size in this lineage of chronospecies that gave rise to Megalodon. This trend began 66 million years ago in the great catastrophe that gave rise to the age of mammals, and ended with Megalodon around 16 million years ago. Research indicates that unlike the macroevolutionary trend of this lineage, which was to increase in size, Megalodon seemed to have reached an optimum or maximum size and stabilized its proportions for a long time. This is because no significant differences in size are found between the first and last megalodons, and no trend of either increase or decrease can be observed over the more than 13 million years that they inhabited this world. They lived from the middle of the Miocene to the end of the Pliocene, a time full of extremely important events for the history of nature. The Miocene lasted from 23 to 5.3 million years ago, when the Pliocene began, which lasted until the Pleistocene 2.6 million years ago. During the Miocene, planet Earth went through a slow and gradual climatic transition, from a hot and humid world with tropical climates and rainforests dominating much of the globe, to a drier and colder world, with large expanses of grasslands and deserts. In the oceans, these transitions were just as profound as on the continents. The closing of passages between the Mediterranean Sea and the Indian Ocean was one of many aspects that redefined global ocean circulation patterns as the waters became colder and more productive. It was during the Miocene that kelp forests emerged, gigantic algae that grow meters a day, fixated to the substrate in shallow waters and equipped with buoy-like structures that ensured they stayed as close as possible to the surface, the source of sunlight. They quickly became some of the most productive ecosystems on the planet due to their insane ability to sequester carbon diluted in water. By the Pliocene, the faunas were much more recognizable, although many things were still completely foreign to our eyes. Among them were giant sloths native to South America, which at the time was living out its last moments as an isolated continent. Incredibly, one of these sloths, Thalassocnus, may have been a potential prey of the Megalodon, since they overlapped in time and space for more than 5 million years. This sloth had a habit of feeding on seaweed in the cold and productive waters of the South American Pacific Ocean, and its size is compatible with Megalodon's preferred prey. But Thalassocnus didn't have to worry solely about Megalodon, since the Pliocene was the time of another group of gigantic marine predators that we'll soon learn about. Although many aspects of their biology are very mysterious and debated, certain characteristics were common to all sharks. Megalodon's teeth, for example, were nothing like ours. Mammals have two sets of teeth during their lifetime: milk teeth and permanent teeth. During the childhood, the permanent teeth form inside the cavities of the skull, descending as it grows and making room for the permanent dentition. This is because we mammals are known for the high degree of specialization of our teeth, each of which has a different shape and function, such as the incisors, canines, and molars. This couldn't be more different with sharks. Although their shape varies subtly depending on their position in the dental arc, they are all very similar and vary more in size than in function. These aren't chewing animals. Their teeth just need to tear off pieces efficiently in order to swallow them whole. Their teeth are also not rooted in the bone, as in our case, but are lodged in the gums, making the loss of a tooth much less painful and worrying. And they lost teeth all the time without it being a problem, because the teeth are organized in rows, and when the front row tooth falls out, the next in line comes in quickly. This meant that they had tens of thousands of teeth during their lifetime, which could last up to 100 years. This explains the abundance of their fossil teeth, as each individual was a huge tooth factory. Its spine would also need to be extremely strong due to the damage we know of due to the form of predation marks on the bones of other animals. Which makes sense, since great white sharks now have the third most powerful bite in the oceans, second only to orcas and saltwater crocodiles. Studies show that Megalodon would have a bite strong and wide enough to consume an 8-ton orca completely in just 3 bites. In addition to the 5 senses we have, Megalodon shared a 6th sense with cartilaginous fish, electroreception. Through the ampullae lorenzini distributed in the anterior part of the animal, they were able to perceive changes in temperature and salinity in the water, as well as electrical signals emitted by living animals moving around. These ampullae are small cavities with sensitive cilia inside and filled with a conductive jaw. However, that wasn't the Megalodon's only possibly acute sense. It's possible that, like white sharks, which, unlike most other sharks, hunt by day, it had excellent color vision, but was also able to see fine details in the dark only under starlight. White sharks also have the best sense of smell in the oceans, with their olfactory bulbs taking up almost 20% of their total brain mass. If this is also true for Megalodon, it could detect odors in minute concentrations in the water in order to detect and pursue prey over long distances. Apparently, Megalodon was not a local predator, but a transoceanic one. This means that during his lifetime, he made long migrations, making the energy efficiency of his swimming extremely important. Although the vertebrae were covered by a superficial mineralized layer, their skeleton would have been nowhere near as heavy as that of a whale or a bony fish of the same size. Estimates suggest that it could swim constantly at around 5 kilometers per hour, reaching top speeds of 40 kilometers per hour during its hunts. It may not seem like much, but for an animal of that size in a medium as dense as water, it takes a lot of strength and energy to move at that speed. This energy efficiency, as well as any energy saving strategy, was more than necessary, since these may have been animals with a much higher caloric demand than most fish. In order to remain active even in colder waters where their prey was abundant, it is possible that these animals produced body heat in the most important parts of the body, such as the digestive system and the innermost muscles. This is observed today in white sharks and is called regional endothermy. Also called mesothermy, this strategy seems to be halfway between totally exothermic animals, which depend on the temperature of the environment and have low energy demands, and endothermic animals, such as mammals, which produce their own heat and can move around even in the cold, but have to eat 10 times more. The immense volume of Megalodon's body may have helped regional mesothermy to be more efficient, minimizing surface area in relation to volume and slowing down thermal exchange with the environment, a strategy we called gigantothermy. This would make it an animal with a gigantic calorie requirement to sustain its huge, internally hot and constantly active body. Perhaps this explains Megalodon's preference for marine mammals, the ocean's fattest prey. Many studies of their ecology, their position in the food chain, and their interactions with other species use indirect methods to infer an ecological relationship between prey and predator, for example, or a competition with other predators. The most abundant clues are teeth marks and even whole teeth embedded in the vertebrae of other animals, mainly marine mammals. When these marks show signs of scarring, they demonstrate a failed predation attempt, but when they don't, it's a good indication of the cause of death. Apparently, Megalodon was a predator with a very broad menu, although it did have preferences. This is because it would be much more energy intensive for it to hunt several small prey than just one large meal. The preference for large prey is also a way of minimizing ecological competition with smaller predators. Larger predators can also choose a wider variety of prey than smaller ones. Despite his gigantic caloric demand, it's possible that they didn't eat very often, requiring them to eat much more than what was needed to get through one day. The fat stored in the liver would ensure enough stored energy for a long time, that is, until the next successful hunt. Although the focus of their predation was highly fatty cetaceans, they were prepared to slaughter and consume practically anything they could tear off pieces of. This makes sense considering that the composition of the marine mammal fauna was different at the time. There were many more species of filter-feeding whales, although none of them were as large as today's, averaging 7 meters in length, less than half the size of a humpback whale, and dozens of times lighter than blue whales. If Megalodon hunted like the biggest sharks do today, it would attack its prey from below and accelerate suddenly, killing with a combination of impact and bite. The impact would be equivalent to being hit by a truck, even capable of breaking the prey's spine, as demonstrated by the best interpretation of an impressive fossil whose vertebrae suffered a sudden and fatal compression. As for the bite, which was extremely powerful and had serrated teeth capable of cutting easily, if it didn't kill the victim immediately, it wouldn't be long before it bled to death in the water. Although filter-feeding whales such as Psychobalena were the preferred prey, there's also evidence of predation or exploitation of the carcass of a physeteroid by a megalodon. Physeteroids are toothed whales more closely related to dolphins, the odontocetes. Today, the sperm whale is the only surviving species of this family, which was once much more diverse. Especially during the latter part of Megalodon's existence in the Pliocene, they established themselves as super successful predators and held the position of largest marine mammal of the time, with more than 15 meters and teeth the size of traffic cones. One individual shows very obvious serration marks from Megalodon's teeth, demonstrating an unusual ecological interaction, a Megalodon biting the face of a physeteroid. This means that there is a possibility that Megalodon would prey even on its direct competitors for smaller prey. Just like today's killer whales, a species with such a wide temporal and geographic distribution must have subdivided into many semi-genetically isolated subpopulations, perhaps each adapted to hunting a different type of prey in a different environment. Most likely, as in today's cartilaginous fish, copulation between them was carried out by inserting the male clasper into the female cloaca. The clasper is a structure analogous to the penis, although very different. It is a forked cartilage, sometimes with hooks, which opens like an umbrella inside the cloaca, inseminating unceremoniously. Instead of laying oddly shaped leathery eggs as many sharks do today, they were viviparous animals, another strategy that is not uncommon in living sharks. In their reproductive strategy, they choose quality over quantity for their offspring. This also means that they had a slow reproductive cycle, having few offspring at a time, even though they were gigantic. This slowness between generations makes animals much more sensitive to extinctions caused by sudden environmental and ecological changes, which may help explain their mysterious and sudden extinction. We know this by studying the preserved vertebral centers, which are a record of their bone growth, the study of which reveals not only the speed and pattern of their growth, but also their size at birth. These studies revealed that the neonates, the newborn pups, were born 2 meters long, a respectable predator from day one. We don't know if they took a solitary course at birth or if they had to move away from their mother quickly to avoid the risk of cannibalism. But it's not impossible that pups were tolerated by adults, following them and taking advantage of the remains of their hunts. But from 2 meters to 20 meters in length, many changes took place. Evidently, this was an animal that certainly didn't eat the same things from the first to the last day of its life. It would need to go through an ontogenetic niche transition, adapt to different prey categories and hunting strategies throughout its development. This would mean that the same species would occupy a series of different ecological roles during its life, which would also mean that it would need to migrate to find new prey throughout its life. Evidence of this was found in an ancient Megalodon nursery in the Gatun Formation in Panama. This geological formation was deposited in an environment of shallow, warm waters, which supported a diversity of marine mammals and more than 16 fossil species of sharks, one of the most common being neonate and young megalodons. It is possible that the juveniles aggregated in these regions due to the combination of favorable temperature for growth, abundance of prey, and rarity of adults, which minimizes the risk of cannibal predation. In addition to nurseries, it is reasonable to assume that they also used areas as breeding grounds and others as feeding grounds. During the Pliocene, the diversity of filter-feeding whales was drastically reduced from dozens of species to just 17. They, which were the Megalodon's main source of food, must have seriously impacted their populations with their extinction. In the Pliocene, we also began to find fossils of the ancestors of today's white shark more frequently, showing that they coexisted with Megalodon. Analysis of zinc isotopes in their teeth showed that they had a niche overlap. They shared many prey in common and occupied surprisingly similar positions in the trophic chain, despite their size difference. But it was also a contemporary of the largest predatory mammal of all time, Leviathan mevieli, although it appeared later and became extinct earlier than Megalodon. Leviathan was a physeteroid the size of a present-day sperm whale, but unlike it, it also had much larger teeth on the top. Its favorite prey was also the small and abundant filter-feeding whales, making it a direct competitor to Megalodon. It's not at all absurd to think that Megalodon could have been vulnerable to predation by Leviathan and other species of giant carnivorous odontocids for much of its life. That would be a very dangerous time to be in the oceans of planet Earth. The last teeth of Megalodon coincide with the transition from the Pliocene to the Pleistocene, 2,006,000 years ago. And that is no coincidence. This was a time of drastic climate change and mass extinction on planet Earth. This is the beginning of what we call the Ice Age, and technically, we are still living in this glaciation. The gradual cooling trend that had been going on for more than 30 million years suddenly worsened, changing the Earth's climate in just few tens of thousands of years. It may seem like a long time, but geologically, that's the blink of an eye. One of the things that may have fatally affected the last populations of Megalodon was the drastic and geologically sudden drop in sea level by more than 120 meters in just a few thousand years. It was caused by the accumulation of water in the form of extensive polar ice caps above sea level and on the continents. This may have destroyed many of their nurseries and weakened their populations, leaving their young vulnerable to predators. The other aspect that may have affected them is the average water temperature itself, which has dropped significantly, as much as it was able to generate heat in certain parts of its body to stay active in cold waters. As we have seen, this is a strategy that requires a lot of physiological energy. This was an animal that preferred warm water for a good reason. It was much more efficient in it, as it would need to produce much less heat of its own. Marine mammals, on the other hand, which are totally endothermic and covered in fat, feel much more comfortable in the icy ocean. The combination of the extinction of its preferred prey, colder waters, habitat reduction, competition with new types of predators, and global trophic restructuring is probably what brought about the end of the largest shark and one of the largest fish in the history of nature. But that doesn't make them any less incredible, since their genus has lasted more than 10 million years, a much longer time than most vertebrates usually last. We know that the extinction of a top predator profoundly affects the dynamics of an ecosystem, so it is to be expected that the oceanic fauna has changed drastically since its extinction, and that's exactly what happened. Since the beginning of the Pleistocene, new species of filter-feeding whales have appeared, including one of the largest, if not the largest animal of all time, the blue whale. We started finding fossils of this species around 2 million years ago, just 600,000 years after the last megalodons, a blink of an eye in geological time. Cold water holds more diluted oxygen gas than warm water, so the glaciation we are experiencing today has made the polar oceans much more productive. The populations of phytoplankton, zooplankton, fish, crustaceans, and marine mammals have exploded. It is possible that in the transition to the Pleistocene, many groups lost in diversity and gained in number of individuals and biomass, of course, before humans entered the scene. The current composition of fauna and function of colossal filter-feeding whales was established almost immediately after the extinction of Megalodon, and most likely as a result of it. These new cold and super-productive oceans, coupled with the absence of a top predator capable of slaughtering colossal prey, have enabled the evolution of filter-feeding whales that defy the limits of physics, ecology, and animal physiology. At over 200 tons well-fed, adult blue whales are almost 10 times larger than Megalodon, although their calves and weaker individuals could still be prey if it existed. Even today, there are people who take seriously the assumption that somewhere Megalodon may be alive, but there is no scientist to support this idea, making it a conspiracy. Many people say that the ocean is basically unexplored, and that some last individuals could exist in abyssal ecosystems. Firstly, the pressure at a depth of kilometers is so gigantic that an animal of that size would be completely crushed. Secondly, there is not enough energy in these environments to sustain an active super predator like this, since there is no light. The primary source of resources in these ecosystems is the rain of organic particles and dead animals that comes from the surface. When whales die and sink, for example, They are quickly consumed in a feeding frenzy so intense that even their bones are consumed within few years. Virtually all abyssal fauna is either living on organic dead matter or sustained by hot toxic underwater chimneys. The idea of this video was to remove the Megalodon from the position of a cryptid or fictitious animal, whose existence is supported only by dubious photos, poorly made videos, and fishermen's stories. So our aim was to portray it as the important, successful, powerful, sophisticated, and definitely extinct animal that it is.